Hello guys, today we're going to talk about error detection, and we're going to take an example on CRC. We're going to explain what's parity bits, odd and even, and we'll see where it's used. Let's see for error detection. What is error detection? Algorithms to detect if there's an error, and mostly this is used in let's say communication, networking. When you send a packet, send a message, we want to guarantee that the receiver received the message without any error, so we need to detect the error, and then we have different algorithms to solve the problem. We'll explain that also. So we had earlier we used parity bits. Parity bits were used, and if you know, if you remember in assembly, there's a register called the flag register, and one of the bits in that flag register is the parity bit. And what's a parity bit? It's a bit that counts the number of ones in a message. Remember, count the number of ones in a message. Parity bit. We have two types of parity: odd or even. Odd parity, number of ones in a message. Let's say this is my message: 1 0 1 0 1 0 0. How many ones do I have in my message? 3. And if I'm using what? 1 2 3. If I'm using odd parity, that's good. I'm not gonna add anything. On my odd 3, my parity bit will be 0. My parity bit will be 0. If I had an even number of ones in an odd parity scheme or algorithm, I'll put the parity bit as 1. I'll set the parity bit as 1, and this parity bit is gonna be what? Is gonna be appended or added to the message. Added, not addition. Appended, like this. This is my message. This is the message, and this is my parity bit. Parity odd, number of ones. I have the even parity, also the number of ones in a message. This is the same message. How many ones do I have? 1 2 3, and I'm using an even parity. So to make it even, 3 is not even, 3 is odd. To make it even, I'll add a parity bit of 1. So I'll have a message, and this will be my encoded word or message, or my new generate message with a parity bit. So think of it. If we were communicating and I want to send you a message, it's this message. I'll count the number of ones. I'll find it's 3. I'll add a 0 here. I'll send it to you. You know that the last bit that I appended is a parity bit, and you know that we're using odd, let's say. All that is going to happen in the handshaking. So when you receive this message, you count the number of what? Ones in the message. This is the message you're going to receive. You find it's 3. Well, that means the message is correct. No errors were. So let's see this. Gaith sends a message to Alex. Here's the message. I append the 0. Alex receives the message, which is what? I have 1 bit. Wrong. Alex counts the numbers of ones. 1 2 3 4, and he has 0 here, and he knows we're using odd parity, so he has to have a 1 here to make it 5 ones, odd parity. So Alex will what? Will drop the message, know it came with an error, and will send me what's called a NAC, not acknowledge, meaning message, something happened to the message, just resend. I resend the message. he'll check again until everything is good. Here's another scenario where Gaith sends a message to Alex, and Alex receives this message. I have what? 2, 3, 5. I have 5 ones, and sorry about that, guys. This here an error. This should be, no, it's right. So what happened here? Okay, I'm missing a 0. In this I'm missing a 0, missing a 0. After the 1, missing a 0. But the 0 is not gonna make a difference. But it's a good example for an error and seeing what happens. So Alex receives this message where he has what? 1 0 1 0 1 0, and he has an extra 1 in the message. So this is right. This is supposed to be right. Those two. So I have an extra 0 on that one. So here's 2 1s, 3 1s, 4 1s, 5 1s. He's using out parity, and he has the parity bit as 0. Nothing's wrong. He thinks nothing's wrong, but what? The message is wrong in 2 bits. This is the problem with parity bits. They don't detect 2 errors. They can only detect 1 error. If only 1 bit was changed, it can detect it. If 2 bits are changed, it can't detect it. Let's see here. We have an enhanced algorithm which is called Cycle Redundant Check, CRC, and that's same as checksum, used for burst data, meaning large data, not 7 bits as the previous example where I used parity bits. It's called it's a systematic error detection. Systematic meaning it appends in a systematic error detection a group of error control bits. This is supposed to be are appended to the end of the block of transmitted data. This group of bits is called a syndrome. So now we don't have 1 bit. We're gonna append a group of bits called syndrome. For example, I have this message, and it's a 7-bit message. And CRC, first thing I need to do, I need to know how many bits am I gonna add. And usually, let's say this message is, I'm the sender, and I'm gonna send this message to Alex. Let's say same scenario. Me and Alex know we use a key, and here's our key, 1101. This is the key. This is the key me and Alex are gonna be using, and we agree on that in the handshaking. This is the key. So let's go here. This is the message. Append key -1. How many bits were? 1 2 3 4 bits. The key is 4 bits. I append 3 zeros. If the key was 5, I'll append 4 zeros. If the key was 6, I'll append 5 zeros. Now we'll do a long division. Divide. I divide this message with the appended. I do it. I don't send it. I haven't sent it yet. It's my message still. And we use an XOR because CRC is considered as, let's say, a polynomial, and we can use mod 2. We're using mod 2. So it's going to be 0 or 1, and this is uses an XOR. An XOR, this, not subtraction. And I'll explain this in a minute when we divide. So I added 3 zeros to my message, and this is the common key or the shared key between me and Alex. I go and divide it. I'm the sender. Still I haven't sent it. I just want to calculate the bits, the syndrome bits I'm gonna add to this. I can't add only the 3 zeros, but those are gonna calculate. So I'll do a long division. I'll have 1, and this, the quotient, is not important for me. Even if you didn't write it down, we're not going to use it. You can do the division without the quotient. So now I'll have 1 1 0 1 1 XOR. Remember, here we're using the XOR, not subtraction. Why? Mod 2 arithmetic. Mod 2 arithmetic we're using. And 1 0, and here's the, remember, this is the 0 1 1 0. It's gonna, when they're different, gonna give me a 1 same 0. So here it's gonna be a 1 1 0 0. So this is the result of the XOR. Now what do? I get this one, and I have what? I'm not gonna use those. 3. Can I divide by 4? No. So I'll put a 0. I'll drop down this 0 again. Now I only need 4 bits too. Doesn't matter the amount. Just look at how many bits you have. 4 bits. So 4 bits. So here I'll have what? A 1, a 1, a 1, and a 0. This, so it's gonna be this without this. So I'll have 3 bits. Take out this one. I'll have 3 bits. I'll take this one down, and remember, XOR. So now I'll do an XOR. This will give me what? 0 1 0 0. So I'll take out those 2. I'll drop down 2 zeros. And now I'll do an XOR. This is going to be what? 1 0 1 0. That's good. I'm not you're not stuck with my handwriting now. So this is 1 0. I'm gonna get just those. Don't look at this now. I'm gonna get this as an answer. 1 0 1. This is my answer from from Explorer, and I'll get the last 0. Now here I'll have what? A 1, a 1, a 1, and a 0. Do I have anything left? No. So now I'll take those 3 bits. I added 3 zeros. I'll take those 3 bits and find remainder. Quotient, not important. I don't care about the quotient. I'm not gonna use it. So even if, and here's the remainder. So I have my message. Now I'll add the remainder, the 3 ones, to this message. Append the 3 bits remainder, which are called the syndrome. Those bits are going to be the syndrome bits, and I send it to Alex. Alex will receive this message. Oops, sorry. Alex will receive this message. What is Alex gonna do? We have an agreed upon key, the key me and him share, which is 1 1 0 1. He'll take that key and divide this by what? Do a long division on 1 1 0 1, and what should receiver receives and does a long division, check remainder equals 0. So Alex, when he has the 3 ones, he has to get zeros as remainder. Let's see, you can go step by step over this, and here's the remainder 0. That means what? Message was right, nothing went wrong in it. If for any reason this was changed, I won't get a remainder of 0 0 0 0. So this is called cyclic redundant check, CRC, and it's useful in networking where what? Where there's a sender and receiver. A sender and receiver. Why? I append 3 bits, I send it, Alex receives it, divide. If he has something, if he found something wrong, he didn't get a 0, that means something wrong. He'll drop the message, he'll send an ACK to me and then not acknowledged, meaning saying that he received the message with an error or something went and he dropped it, and I'll resubmit the message again to him and he'll check it again. If he gets 0, he's done. It's an error detection, not a correction. It doesn't correct. Useful in networking where I explained that. There's also what's called Hamming distance. I don't know if I'll have time to post it today before your exam tomorrow. But there's one I did it on the board and I have a video for it. Hamming distance. Check it, really, it's important. Hamming distance, it's an error detection and correction. It corrects the error. And how is that done? If, for example, I had this message and I'm gonna add, let's say here, what do I have? 1 2 2 0 2 1 2 2 2. I'm gonna add 4 bits to this message. If I was using Hamming distance, I'll explain it. It's a little bit complicated, but I'm gonna add 4 bits. I'm not gonna add them here. What's good in Hamming distance, I'm gonna spread them inside the message, and that makes it more reliable. That's why Hamming distance is used more where I have 1 copy. If a DVD, if the DVD got scratched and you need that data important on the DVD, that's what they use, a Hamming distance, where it can detect an error and correct it, and it can correct more than 1 error depending on how many bits I'm using, and it's really useful in hard drive where I have an errors in hard drive where I have just one copy. It's not in communication. It's more complicated. It needs more processing time, and remember, networking and communication, time is important. Hopefully this was useful, guys. If you have any questions, please let me know. Sorry it was quick.